Timbo, or give us out there? Welcome everybody to this night's lecture. Please give a warm welcome to Professor Helen Pask of Physics and Lasers at Macquarie Uni. I had the pleasure of getting to know Helen and of course a family over the last, 12 years.
Mm-hmm. Yep.
My main astonishment is Helen is an ordinary lady doing amazing things. When I asked Helen's husband Andy about sailing in boats, which we talk about nearly every week, it all comes back to Helen and Andy sailing a 26-foot steel boat from England to Australia. The two of them on Wandering Star.
Mm-hmm.
Took them 11 and a half months. And one of the stories is that over the Atlantic Ocean, forestay broke, didn't it?
Yeah.
And Andy thought, I'll just get up there and replace it. But Helen couldn't hoist him up because he was too heavy. So Helen got up in the middle of the Atlantic and replaced the forestay. So yes, Helen volunteered and that was it. So please welcome Helen and enjoy the lecture.
Thanks, Jeff. And certainly sailing from England to Australia was a good lesson in project management, and helped me get where I am today. Okay, so I think you've had a couple of other speakers from Macquarie Uni in the past year or two, I've heard. So we do lots of great stuff at Macquarie, and I think you've had Graham Town speak to you last year. Graham's in the Department of Engineering. We're in the Department of Physics and Astronomy. That's one story up. But I do know Graham reasonably. One story up, not one level up or anything like that. Okay, all right. This is a quick, I did and ah about what I should talk to you because I've done lots of talks to school kids. I've done lots of talks to physicists who may or may not know much about lasers, and I think that you're some of you will be electrical engineers or electronics engineers or just hobbyists. You're all going to be great at building stuff. So I've tried to put something in here for everyone, and I've brought along a few bits and pieces that we can look at and a few demos and things. So I thought I would try and cover, what's a laser and what can you do with lasers, because not everybody might know about those things. So I'm an academic at a university. What's my job? I thought I'd just speak not too much, but just a little bit about, what we do in those ivory towers, and I'd talk to you a little bit about a couple of my research projects, which happen to be Raman lasers and terahertz lasers. And I'm used to using a laser pointer, but I'll use an aerial instead.
That's a radio frequency one.
Awesome. Well, this is why I chose to talk about terahertz lasers, but we'll get there. Anyone heard of terahertz? Okay. Yeah.
Earlier today.
All right. Good-o. Okay. We had a blackout today at work, so that's my excuse. I haven't actually put in the acknowledgement slide that talks about all the different people that have contributed to my work. So obviously this is not all my own work. I work with a team of really, really great people, and I haven't really attributed them all here because they're just names. They probably don't mean a huge amount, but yeah, there's probably presenting the work of maybe 10 or 12 people. Okay, and I just wanted to work this one. And this is a picture of Wandering Star leaving the coast of Spain, heading off for Porto Santo, which is Portuguese island. Okay, so I'm going to come back to the research in a minute. So let's just start off. I said I'm in the Department of Physics and Astronomy, but at Macquarie we have an awful lot of researchers working in the area of light and photonics, and we have a grouping called the Macquarie Photonics Research Centre. Okay, lasers and their applications have been alive and well at Macquarie for at least 30 years. The Photonics Research Centre kind of captures some of that early work, and it's just expanded hugely in the last few years. So there's about 35 staff and about 40 postgraduate students. This is a fairly old photo. You can see there's, looking out there, hello, at the back there. There's not too many girls in this audience, and there's not too many girls in physics, but it's something that we're seeking to improve, and you can see that we're probably about 15% female, I guess, at the moment. But this is the staff and the students, and they all work on different things: laser physics, engineering of lasers, remote sensing, nonlinear optics, quantum physics is a big area at Macquarie. So is biophotonics, people doing trying to put photonics on a little optical chip that can get used in medicine for pathology and things like that. A lot of micro-machining. I've got an example of that coming up. So that's our kind of group, and now we can get on to, well, what's a laser? And I'm sure that, you probably all know a laser's an acronym for laser amplification by stimulated emission of radiation. Actually, when that acronym was introduced, they were really looking for an acronym for light oscillation by stimulated emission of radiation, but that would make the acronym loser, and so they had to. They didn't want that. They had to tweak it a bit, as you do with acronyms. Okay, so this is some work. Yeah. Okay. All right. So this is my snapshot of how a laser works. You don't really have to understand this to follow the talk, but basically, what makes up a laser? Well, you need a laser gain medium. Okay, you can use many different types of media exist: gas, liquids, and solids. In all cases, the laser gain media they emit distinctive. They have unique spectra, if you like. They all emit at different wavelengths. Okay, you need a means of exciting that laser medium. So over there, that can be a flash lamp, a laser, the sun, some electrical current, or even a chemical reaction. Usually it's another light source, or it's an electrical current in the case of semiconductor lasers. And then you have these active ions in the laser material, and it could be, neon, or it could be an ion such as neodymium or chromium in the case of ruby. Okay, and this stimulated emission of radiation bit means that you've got one of these ions, the pumping puts it up into an excited state, another laser photon comes along, stimulates it to emit a carbon copy, if you like, of that incident photon. So initially you have the laser photon incident on the excited atom, and after this amplification process, this excited atom drops back to its ground state or a lower level, and the copy comes out along with the incident photon. So that's stimulated emission of radiation in a nutshell. So you've got this amplification process. You've got one photon in giving you two, and then those two will produce another two each. They'll amplify each other, amplify up. And you also have a pair of mirrors. They're those blue rectangle things, and they trap the laser photons in the cavity. Okay, so the photons are going backwards and forwards. They're amplifying exponentially, and one of them is a little bit leaky, a little bit transmissive, and out comes your laser beam. Okay, so yeah, I said that the laser gain media emit distinctive or particular frequencies of light, and it depends on what they are. So here we've got an ultraviolet light source incident on a range of different dyes, and this just highlights the fact that different compounds will actually, produce different lines. So if you want to make a yellow laser, you choose a particular gain media. If you want to make a green one, you choose something different. So that's just a little illustration of that. Okay. Right. The first laser looked something like this. Okay. So the first laser was made by Theodore Mayman in Bell Labs, I think it was. Actually it wasn't 50 years ago, because this is actually a picture that I've pulled off a presentation from 2010. So it's now, the laser's now 57 years old, I guess. May 1960, and it was a ruby laser, and it looked very similar to this one here. You can see the same coil of glass here. You can come up and have a look at it later. There's a ruby rod down there. This one doesn't work anymore. Did once upon a time. And there's a couple of mirrors here. You know, really simple. You can knock one of these up in your shed. And when I started doing my PhD in the late 80s, you know, there were scientific American articles on, you know, how to build a carbon dioxide laser in your garage or a helium neon laser. And, you know, people were doing this stuff, which was great. Okay. So what are some of the properties of laser light? Well, I brought along my arsenal, okay, to illustrate some of these things. So, where shall I shine them up there? Oh, it's too much light around here. So, you've seen, everyone see the red one? Yeah? Okay, nothing exciting about that. Most people have probably seen a green one as well, a bit more power in that green one. Here's a blue one. So my first point is that laser light's monochromatic, by which we mean it has, you know, it's a very pure colour of light, isn't it? It's and this is due to the discrete energy levels that make up those excited ions. It goes back to the demonstration with the dyes. What else? I should have hidden that, shouldn't I, and tried to make you guess like I do with the school kids. But, you know, I'm holding the green laser pointer, putting the beam on the wall over there. This one stopped working and I had to operate it, and it's not a very nice compact spot anymore. It's a bit daggy, isn't it? It's got two spots. Something's misaligned, but still putting out plenty of power. But, yeah, laser light has very high divergence, and what you see here is a laser guide star. So a lot of bigger observatories have a guide star associated with them that shoots up into the mesosphere where there's a lot of sodium ions, and the yellow light's absorbed, and it kind of creates an artificial star up there, and the astronomers can actually image that star, and the quality of the image that they get depends on the atmospheric perturbations to the beam, and then they use adaptive optics to actually correct for that so that they get the nicest, tightest spot that they can, and that's for the artificial star that's beyond the atmosphere. You can only do that because lasers are very directional. By the way, what's between the laser pointer and the spot on the wall? Yeah, air. So why, if there's, can you see the beam between here and there? Yeah. It's no Raman scattering. Well, maybe an insignificant amount, but the point is that, you know, you make to the kids is that you only see the laser beam when there's something to scatter it into your eyes, right? So if we can you see it now? Usually you need an assistant to do this, but I think you can use your imagination anyway. Oh, there you go. Okay. So you need something to actually scatter the light so that you can see the beam from the side. Now there's something else. So that's two key properties of lasers. The third one is a little bit less familiar to many people, and that's called coherence. So by the nature of that stimulated emission process, and I said that each photon that's created is a carbon copy of another one that was incident on that excited ion, we say that the laser light waves, or you can think about them as photons, they have the same phase. That just means that they're all going up and down together. For some applications, doesn't matter at all. Doesn't matter for the guide star, doesn't matter for a laser pointer. But if you want to make a hologram, then it matters a lot. And so you have to have this coherence for some types of measurements, interferometry, things like that, and for making holograms. Now, if you came to visit me in the physics department, which is upstairs from the engineering department, okay, you'd find we've got something that they don't. So? We have quite a unique boardroom, okay? And, well, if you come along at the right time, it's quite unique anyway. It looks unique. It's actually quite ordinary. But we have 3 holograms. So our room was specially constructed to have 3 large windows, and in each window is a hologram made by a woman called Paula Dawson. which is an artist who makes holograms, and these are some of the largest holograms in the world actually, and they have the largest depth of field, so they're actually really quite special. And the hologram's called, it's a series of 3 plates called To Absent Friends, and this is a picture of it here, which doesn't do it justice, but when you look in there, and you're welcome to come and visit me and have a look, it's actually like you're looking into a bar, and there's glasses hanging down from here. This is a terrible reproduction actually, terrible photo. There's a dartboard, there's a pool table, there's lots of bottles of grog along the front, Christmas decorations, and each panel is a different time on Christmas Eve. It was made in the basement of the National Acoustics Labs in Chatswood in the, I think it was in 1989 actually. So that's a story that goes on from Coherence.
They're transmission holograms.
They are.
Because I've seen them when she did the exhibition at Funfun. Like she had them illuminated with copper vapor.
Okay, all right.
Green and yellow.
Yeah. Did she have the bar ones illuminated?
She had the bar, which it was that was yellow. That's why.
Okay.
She might have. I think she's got a series of them.
Okay. Yeah, so the bar's best illuminated in the red. We've had lots of exhibitions at Macquarie. She's actually donated all these holograms to Macquarie. I remember Paula, I've known her since I was doing my PhD, and she'll come out and she'll illuminate her holograms with all different colours of light and things. But yeah, she's a pretty interesting person. It's nice that you've seen them. Yeah. Okay, so what's the biggest laser on Earth? Well, guess what? It's in America. Okay, and it's the building that houses it. It's as big as a football stadium, and it's actually not one laser. There's 192 laser beams, and it's all about nuclear fusion, trying to realise nuclear fusion. When I was doing my PhD, I used to go to conferences, and they'd be talking about, you know, laser fusion towards break even, heading towards break even, getting closer to break even, and they're not there yet, but maybe they will get there. Okay.
National ignition, isn't it?
Facility, yeah.
Then you've got Lawrence Livermore.
Yes, yeah, and Lawrence Livermore, some of my colleagues, so Macquarie used to do quite a lot of work on metal vapour lasers, like copper, and they were using copper at Lawrence Livermore as their laser sources. Okay, and then we have somewhat smaller lasers, so I've just got a few examples of where lasers are used. Of course, they're used in CD players, and you can have a look, and without too much difficulty, you can find the laser. Lasers are used for communications. You can, you know, I'm not going to explain how that works because I think most of you would know. But here's my demo of a optical fibre, and you know, shine the beam in one end and comes out the other. If the lights are out, you can actually see the beam doing a bit of bouncing down here, total internal reflection. So some optical fibres most work these days by total internal reflection, and the beam bounces down the fibre. There's another type which is uses gradient index fibres, where the glass is specially designed and the refractive index changes from the centre as you go out to the edge. You know, that's kind of occurred to me, well, there's a similarity there to the way that that radio waves, you know, bend and bounce off different layers of the atmosphere. So, right, and you can, there's a lot of work at Macquarie using lasers for micromachining. So yes, you know, you can cut and weld lots of things with lasers, like car bodies and things. This is a hole that's been drilled in the side of a human hair. This is a tiny little gear that's been cut out of a bit of plastic using a laser, and that's the scale is 100 microns there. The hair is about 25 microns. And here we've got the Sydney Olympic torch. Okay, so Macquarie got a contract in, you know, well, leading up to the Sydney Olympics to make the nozzles in these torches that the gas flows through before it's, you know, to adjust the flow before the torch is lit. There's a picture of the nozzle. There's a picture of the hole in the nozzle. They had to be 78 micron diameter to get...
My son did work experience at Macquarie there when they were doing that.
Oh, what's his name?
Brian Park, but he was 18 at the time. He's got a PhD himself now, but
Okay.
he was saying no, he was saying that one of the guys that was actually at Macquarie and doing it actually did an apprenticeship as a plumber. And he went on and on and on and on.
Okay.
And he finished up doing that drilling in those torches.
Yeah, okay, all right. Yeah, there's a lot of history. So I wasn't involved in the drilling, but I was in the same lab as it, because back in those days there weren't so many of us around. But yeah, no, it's fascinating, and you know, it's a small hole, isn't it?
Oh.
But the tolerance is really interesting as well. So it had to be 78 microns, and I think it was plus or minus 1.5 microns was the tolerance. Because, you know, you can just imagine, can't you, if the hole's too big, you know, the gas will flow out, and the gas is, you know, you've got this little canister here, okay? So your hole's too big, you know, your flame might go out before you reach the next runner, and what happens if it's too small? And the wind comes up, you know, that's not going to look too good on TV either. So, and yeah, so they did the Sydney torch, and anyone know what this one is? No? This is Athens. This is the Athens one. So they got the contract to do the Athens torch as well. And it's not just one torch. So every runner had a different torch. So there was about, I think they drilled 11,000 holes or 11,000 nozzles or some amazing number. Do you know the number? Remember how many torches there were? There was a lot. Okay, what else are lasers used for? Well, you can use a laser, a short pulse of laser light to measure the distance from the Earth to the Moon. Okay, right, it's not here. How long do you think it takes for the pulse of light to travel to the Moon? 2 seconds round trip, okay, that's right. And of course, it uses these prisms that were left there. There's an array of prisms, and this is still sitting on the Moon, and they're down to a few millimetres, and I think that's safe. They keep improving it anyway. And lasers are used to measure the water depth along the coast of Australia. So this is technology that came out of the Defence Science and Technology Organisation, which is now DSTG, where the organisation's been replaced by a group. And basically, you can see that there's a green and a yellow beam. A red and a green beam. The red bounces off the surface, and once again it's a pulse. So you look at when that little pulse returns in time. The green goes in, a little bit of it bounces off the seafloor, and about 1 in a million photons will actually come back and get detected in the flame. And it's the difference between the green pulse returning and the red pulse returning that lets you work out how deep the sea is. And all this information, so you can see that they scan huge areas of the coast. I think there's one plane that's always flying. It's operated by a company called Fugro now. And that information gets fed to the hydrographer's office and forms the basis of electronic charts. And lasers are used a lot in medicine, and this is actually my lab, and so I'm going to come back to this one, okay? So, what's my life like? Well, so, actually, I've said research academic. I'm very fortunate because probably for most of my career, I've been able to survive just doing research, okay? And that's been pretty wonderful, but that's come to an end because, winning research fellowships is quite difficult, and it becomes more and more difficult as you go on. And so when I became a professor, I've also become a teacher, and so like most of our academics in physics and astronomy, I spend 40% of my time on research, 40% on teaching, and 20% on this thing called service, which takes many different forms. So thinking about the teaching and the service, what do I do? Well, I'm the director of the first year physics lab, so we have about 1,000 undergraduate students come through our first year labs each year. I'm going to be lecturing to first year students, taking physics, engineering and chiropractic science this year. I'm going to be convening a new PACE unit. Macquarie's got this thing called PACE, and they want the students to go out and have some real authentic experiences in the workforce. So I'm putting together this course which will see the students PACE in a whole range of different types of workplaces, and it's pretty much the last thing they do before they complete their degree. And there's lots of other things, and I'll just highlight this one in the open work. This is an annual thing at Macquarie. It's on the 20th of May. was Nicholas Swan has been the telescope today. Okay. Okay, great. So, you know, you go along and the people set up the telescopes in Parker. Good night, the big laser beam shooting up into the sky most years. Hopefully it's done again this year. So, Saturday night, if you've got nothing better to do on the 20th of May, you might like to come and have a look. And then on the research tab, you know, what's the research, what's the academic possible in that? The universal question. Where's your working for? Are you at a firm? You've got class? Pain in the neck? But, you know, typically most go out and get weight bloods themselves. That's a really big part of my work. I like talking on it. I don't want to talk about it, but I don't want to talk about all of it. Okay, and I want to talk about the way that I work as well. And that's, you know, a lot of my colleagues are quite similar in their outlook. And that's a big change from, you know, over like 20 years or something where it was almost to be, you weren't a proper scientist, you know, that was framed up to the ivory towers kind of thing, and, you know, you're kind of a little bit second class if you're engaged with industry, but that's one of the things that always motivated me, and I think in pretty much all the universities, there's a lot more emphasis on that. You've got to be really careful, don't you, because today's pure science is tomorrow's applied science. And so, you know, that's a novel debate. And, you know, for some of my colleagues, yeah, it's actually the topics of research and the way that, you know, people become aware and pick up and build on that science is really important. I think you've got to understand what they need. So yes, there's lots of industries that say, I've worked at this university and it just didn't work, you know. So I think, you know, the universities are trying. I mean, I've seen both sides of it, right? So I've come up with some great partnerships and, you know, sometimes it's the companies that you know, just something comes up, takes too long, you know. The fault can be on both sides. But yeah, no, universities got fantastic schemes for, you know, helping us to engage, attract industry partners, but then when it comes to drawing up the contracts and things like that, that's when things can fall over. But I think we're getting much better at it, and you can't, as a researcher, if you really want this to happen, you've got to get right in there and you've got to go and visit the partners, understand their needs and facilitate this process, because hopefully their finance people who work with your finance and contract people, it's very vulnerable and doesn't work sometimes. So now I get on to my research, okay, and I've kind of got three projects, right? One of them is actually called Raman lasers, and this yellow laser, which is now, is that R-A-M-A-N or is that R-A-M-E-N? Yeah, that just reminds me of when my husband Andrew and I went skiing in Japan, you know, ramen. So we walk into this little restaurant and it's called ramen hut, something like that. And Andy says to the guy, because there's just one person in there, and asked, and he said, are you Mr. Ramen? That goes back to the late 80s as well, so, you know, we're far more sophisticated in our cuisines, and I didn't know what ramen noodles were then. But ramen lasers, terahertz lasers, which are about as close as a laser gets to a radio wave. Okay, and I've got this other biologists, they have much better time. They're chasing butterflies and climbing mountains. What can I do? So anyway, I did it. So that's the project where we're it's a project looking at remote sensing of water temperature and salinity. Okay, so we go out in this boat, we shine a green laser pointer, big grown-up version of this pointer, into the water. We look at a signal that comes back. Just a tiny little bit of the light comes back in the red, and we analyse that, and we can work out what the temperature is. These are really the thermometers, but you can work out what the temperature is. But what's really interesting is then if you have a pulse laser, a short pulse of light, you analyse what comes back as a function of time. It gives you temperature information as a function of depth and salinity, and that's really exciting